And you may be curious how to obtain the solution y of t. So I will show you the derivation to obtain the solution of critically damped response. So in this case, the damping ratio zeta is 1. The transfer function is given, which is y of s over u of s is omega n square over s square plus 2 zeta omega n s plus omega n square. Since zeta is 1, the transfer function becomes omega n square over s square plus 2 omega n s plus omega n square. This is omega n square over s plus omega n square. Y of s is omega n square over s plus omega n square times the unit step 1 over s. To find the solution of this, we can do the partial fraction expansion. A over s plus b over s plus omega n plus c over s plus omega n square. So a can be obtained from s times y over s and evaluated at s is equal to 0. Then omega n square over s plus omega n square, s is equal to 0, then 1. So a is 1. Let's find the c first. C is s plus omega n square times y over s, and s is equal to minus omega n. Then we have omega n square over s, s is minus omega n, then we have minus omega n. And b, we need slightly different equations. d over ds, s plus omega n square times y of s, s is equal to minus omega n. So this one is d over ds, omega n square over s, s is equal to minus omega n, which is minus omega n square over s square. S is equal to minus omega n. Then we end up having minus 1. Okay. So this one so you can study this part in page 96 in the main textbook. The partial fraction expansion with the case of that G of s has multiple order poles. As a result, we have y of s as 1 over s minus 1 over s plus omega n minus omega n over s plus omega n square. Then what? we can take the inverse Laplace transform, then we can obtain the solution which is 1 minus e to the minus omega n t 1 plus omega n t. Let us look at transient response specification. First specification is percent overshoot. Percent overshoot is defined by the maximum output minus the final output over the final output times 100%. So basically this is the percentage of the maximum value of the output based on the final value of the output. And also percent overshoot is related with the damping ratio. So the equation will be e to the minus zeta pi over square root of 1 minus zeta square times 100%. Also we have rise time, which is the one of the transient response specifications, and we denote the rise time as TR, and the rise time can be approximated by this equation 1.8 over omega n. So the definition of the rise time is so the time for the step response to reach from 10% to 90% of its final value. And also we have to consider the peak time denoted by TP, and this can be obtained by this equation pi over WD. And we know what is WD, right? This is omega n times square root of 1 minus zeta square. So basically this is time to peak. Another specification is percent settling time. We can define the settling time with 2%, 4%, or any number you want, but we usually use 2% settling time. We denote the settling time as TS, and which can be approximated by this equation 4 over zeta omega n. Let's look at this figure, the transient response specifications for the second order system. So there is a y max and y final. So the percentage of this amount will be the percent overshoot, and the rise time is the time for the step response to reach from 10% to 90%. of each final value, and peak time is time to peak, right? 2% settling time is the time required for an output to reach and remain within 2% of its steady state value. So if you look at this equation, for the percent overshoot, you can notice that the overshoot is depending on the damping ratio zeta. So let us look at the relationship between damping ratio and overshoot. Percent overshoot is the function of the damping ratio only, right? If you look at the equation, percent overshoot is e to the zeta times pi over square root of 1 minus zeta squared times 100%. So we can see that bigger damping ratio will introduce smaller overshoot. So usually if damping ratio is 0, then overshoot will be 100%. We already studied that the undamped system is just oscillating, not converging to any value. So the percent overshoot is 100%. And then as zeta increases, the overshoot will decrease exponentially, and when zeta is 0.7, the percent overshoot is 5%. The transient response specification also based on the pole locations on S-plane. Let us consider the typical second order system. The transfer function is this one. In this transfer function, the characteristic equation is s squared plus 2 zeta omega ns plus omega n squared is equal to 0. Okay, so from the root of this characteristic equation will be the pole location of the system. We can consider the three cases of pole locations with respect to the damping ratio. So first case is there is no damping, and second, the damping ratio is 1, and lastly, we can consider the damping ratio is larger than 0 and less than 1, so underdamped system. So in this case, the pole location is what? Pole location is plus minus omega n j. So there is no real part, only imaginary part. And when zeta is 1, then we have repeated pole on the real axis, minus omega n and minus omega n. And for the underdamped system, we have pole location with minus zeta omega n as the real part, and plus minus omega n times 1 minus square root of 1 minus zeta square j as a imaginary part. If I plot the pole locations on the S-plane, so here we have real axis and imaginary axis. When the zeta is 0, then we have poles on the imaginary axis. And when zeta is 1, critically damped system, the pole location is on the real axis, and which is repeated pole. If zeta is between 0 and 1, then pole will be like this one. So this is this case, and in this case, the imaginary part has this value, and then real value is minus zeta omega n. We can easily see that this length is omega n, and we denote this angle as a phi, and this angle has some relationship with the damping ratio, which is sine phi is the damping ratio zeta. So as you can see, if zeta decrease, then phi decrease, and zeta increase, then phi increase. In other words, if I draw the S-plane, so the pole move this way when zeta decrease, and pole move this way when zeta increases. Also, if phi is 45 degree, then the zeta is 0.7. Let's think about the settling time based on the pole location. We already studied about the first order system. We know that pole is minus 1 over tau, right? Smaller tau will make the pole move to the left. It means the system will be faster, right? So basically small tau means the system gets 63% of the final value quickly. It means system is faster. Also, if pole is further from the imaginary axis, then it's the same as tau is small, then the system is fast. Let us look at this more analytically. So first order system transfer function is 1 over tau s plus 1, and I'd like to find the 2% settling time. So we know that the response of this first order system is 1 minus e to the minus t over tau, and 2% settling time means we want to find the time. We want to find the time gets 0.98, right? Because that's the definition of the 2% settling time. From here, e to the minus settling time over tau is equal to 0.02. If I take the log, then minus settling time over tau is log 0.02. The settling time over tau is minus log 0.02, and this is log 1 over 0.02, which is near 4. As a result, 2% settling time of this first order system can be defined by 4 times tau. You can do the similar procedure to find the 2% settling time of the second order system. If I denote the pole location on the S-plane, then we know that the real part of the pole location is minus zeta omega n, and 2% settling time will be intuitively 4 over zeta omega n. Again, here, if the pole moves to the left from the imaginary axis, then zeta omega n will be larger. It means the settling time will be smaller. Here I present several figures about the unit step responses of second order system. As seen in these figures, the response becomes more oscillatory with larger overshoot as damping ratio decreases, When the damping ratio is larger than or equal to 1, the step response does not exhibit any overshoot. It means the response never exceeds its final value. The effect of damping of the second-order system on the characteristic equation roots, which is poles of the transfer function, is illustrated by the third figure. The imaginary axis corresponds to zero damping. It means the damping ratio is 0, and zero damping results in sustained oscillation response, and the system is marginally stable or unstable. So as you can see that the location of characteristic equation roots, which is again poles, plays an important role in the time response of a second-order system. In practical applications, only stable systems that correspond to the damping ratio is larger than 0 are of interest. From the last figure, you can see that more transient response characteristics based on the pole locations. So if the pole location moves upward with the same real part, then the envelope of the response will be the same. If the pole location moves to the left from the imaginary axis horizontally, then the frequency of the response will be the same. If the pole location is moving with the same angle phi, then the overshoot will be the same. It means the damping ratio, which is zeta, is the same. Next, let's talk about dominant pole. So before I actually talk about dominant pole, let me show you an example. Let us consider the system with this transfer function 10 over s plus 1 times s plus 10, and the input will be the step input. Okay, so from here we can define the y of s as 1 over s minus 10 over 9 1 over s plus 1 plus 1 over 9 times 1 over s plus 10. If I take the inverse Laplace transform, then the output will be 1 minus 10 over 9 e to the minus t plus 1 over 9 e to the minus 10 times t. So let's say this response as A, this response as B, and this response as C. So the total response of this system is A plus B plus C. So if I draw the response, we have response A, which is just 1, and we have response B, which is from the minus 10 over 9 when time is equal to 0, and then it becomes 0 as time goes by. Okay, and we have another response, which is C, from 1 over 9 when time is equal to 0, and then it converges to 0 very quickly because it's e to the minus 10 times t. So this is C. Then the total response is from here and looks like this one. So this is the total response y over t. What can you notice from this example? So the total response looks like just the combination of A and B, because the response C is quickly decaying to the zero. In other words, the influence of C is very negligible to the total response. So if we look at the co-location of the transfer function, we have two poles, one at -1 and the other one at -10. So basically this pole is slow and this pole is fast, right? Since the response of this pole location is very fast, the response due to this pole is negligible. So the response due to this pole is negligible to the total response, and we call this pole as dominant pole. So we call the pole which is the most closest to the imaginary axis is called dominant pole, and if the value of the real part of the dominant pole is sufficiently larger than other poles, then influence of the other poles to the total response is negligible. Then you may ask me how large a pole is considered to be really large. How large a pole is considered to be really large. So in practice, if the magnitude of the real part of a pole is at least 5 to 10 times that of a dominant pole, then the pole may be regarded as insignificant. Okay, so 5 to 10 times. Let us talk about two types of systems. Minimum and non-minimum phase systems. Minimum phase system means no poles or zeros in the right half plane. Basically stable system without zeros or with zeros in the LHP. So we have looked at the system's performance based on the pole location, and let us look at the effect of minimum phase zero. So here, let's look at some example with step input. So system 1 has the transfer function, which is just 1 over s squared plus 2s plus 1. So in this case, this is a minimum phase system without any finite zero. Then y of s will be 1 over s squared plus 2s plus 1 times 1 over s. And system 2 has the transfer function as 2s plus 1 over s squared plus 2s plus 1. So basically, the system 2 has the same characteristic equation as system 1, but the system 2 has 0 at minus 1 over 2, which has minimum phase 0. As a result, y of s is 2 over s squared plus 2s plus 1 plus 1 over s squared plus 2s plus 1 times 1 over s. So as you can see, these parts are the same, but system 2 has additional term due to the minimum phase 0. If I draw the system response of the two systems, so if I draw the system response of the system 1, then it will look like this one. This is a system 1. Because if you look at the transfer function, the system has the damping ratio as 1, so critically damped system. There is no overshoot. System 2 will be the combination of this system 1 response with the response due to the 2 over s squared plus 2s plus 1. So this is the 2 times of transfer function. So this is impulse response So this is the 2 times impulse response of 1 over s squared plus 2s plus 1. Then the total response of system 2 will be something like this one. So this is system 2's response. So from this observation, the left half plane 0 or minimum phase 0 induces more overshoot, and the LHP0 has no effect on the settling time. Then let's talk about non-minimum phase system. So non-minimum phase system means at least one pole or zero in RHP. I will just briefly talk about the characteristics of non-minimum phase system. The non-minimum phase system often associates with delay, and also it is harder to design controller. Later, when we study about the frequency analysis, then I will talk about this part more detail. One of the most important performances of control systems is steady state error. One of the objectives of most control systems is that the system output response follows a specific reference signal accurately in the steady state. For example, a pick and place robot arm must end up accurately in the desired position to pick or place an object. In the real world, because of friction and other imperfections, and the natural composition of the system, the steady state of the output response seldom agrees exactly with the reference. In practice, the steady state error is unavoidable. First, I will show you the steady state error of open loop control system, and then I will introduce. Let us consider the system with the transfer function of 1 over s plus 5 and input which is 3 times 1 over s. So the desired value for output is 3 in this case. Let's look at the output y of s, which is the transfer function times input u of s. Then this is 1 over s plus 5 times 3 over s, so s plus 5, 3. So we can find the steady state value using final value theorem. So limit s goes 0, s times y of s, which is what? Which is 3 over 5, which is 0.6. So our desired output value is 3, but the final value is 0.6. So the steady state error is 3 minus 0.6, which is 2.4. So basically, using the open loop control, we cannot achieve the desired value of output and we need feedback structure to obtain the desired value of the output. Next, let's consider feedback control. So we have R of t here, and then some controller, and system G of S, output Y of t, and feedback signal. And then let's say our controller is just K, which is constant. Then the E of t, this one, the error is R of t minus Y of t. If we take the Laplace transform, E of S is R of S minus Y of S. What is the Y of S? Y of S is K times G of S times E of S. So from here, E of S can be defined as 1 over 1 plus K G of S times R of S. So steady state error, we use ESS to denote the steady state error, is equal to limit S goes 0 S times E of S. Okay, so again we can use the final value theorem to directly compute the steady state error. So again, if we think about this example, then the E of S is 1 over 1 plus K times 1 over S plus 5 times 3 over S, which is S plus 5 over S plus 5 plus K times 3 over S. Let's say our controller K is 145. Then E of S becomes 3 times S plus 5 over S plus 150. Okay. Then the steady state error ESS is limit S goes 0 S times E of S, which is 3 times S plus 5 over S plus 150. So S cancelled out and 0, 0, which is 15 over 150, which is 0.1. Previously, using open loop control, the steady state error was 2.4. Then the steady state error is 0.1. So as you can see, using the final value theorem, we can obtain the steady state error, and we can easily predict the controller performance. Based on this, we can analyze the system and design better controller. So in the next class, we are going to look at what's the effect of the disturbance and how to minimize the effect of the disturbance using controller. Also in this lecture, I just showed you the controller with constant gain K. We call this type of controller as a proportional controller, in short, P controller. Later, we are going to study different structures of the controllers, such as proportional and derivative control, proportional and integral control, and proportional, integral, and derivative control, which is PID control.